In this tutorial video, we're going to be talking about objects in the solar system. We're going to be talking a little bit about our galaxy, the Milky Way, and what our galaxy is. And we're going to be talking about why objects in the universe orbit other objects. This goes together with the work that you did on redshift and the Doppler effect and fusion in stars and the star life cycle to make up the space physics topic and the OCR GCSE. So when you're doing your notes on this topic, try and put it in with those other notes. And if you have any questions, please ask. Okay, so to start with, objects in the solar system. There are 3 key objects that the exam board want you to know about. There are tons of other objects, but these are ones the exam board want you to know about. If you want to know about the other ones, probably a really good website to have a look at is the NASA Near Earth Object Resource Centre, and it will tell you all about the difference between meteorites and meteors and asteroids and comets. Really interesting. But in the meantime, we need to make sure that we are happy about what a planet is, what a moon is, and what a dwarf planet is. So planets, it's a large body that orbits the sun in our solar system. Planets do not produce their own light, they reflect the sun's light. Now, within our solar system, we've classified the planets in our solar system into 2 different groups. So we've got the inner planets and we've got the outer planets. The inner planets are closer to the sun, the outer planets are further away. The inner planets in our solar system all have solid rocky surfaces, and the names of the inner planets are Mercury, Venus, Earth and Mars. Now the outer planets that are further away from the sun tend to be very large. They're much, much larger than the inner planets. They are made of gas, so you couldn't land on the surface of them. And they are Jupiter, Saturn, Uranus and Neptune. So those are our planets. Then, orbiting around some of the planets, we have moons. So moons are natural satellites. So a satellite is anything that orbits around something else. And a natural satellite means that it's naturally made rather than man-made. So some of the planets have got moons. They're natural satellites in orbit around a planet. Moons can be very large. Don't think of moons as something that's necessarily small. Jupiter's got some moons that are bigger than Pluto. Okay, and then finally, talking of Pluto, we have dwarf planets. Now these are there's loads of dwarf planets. The most famous one that we know about is Pluto, because it used to be classified a planet and now it's being classified as a dwarf planet. So dwarf planets are quite interesting. They have enough mass and gravity to be round, unlike asteroids, which are all sort of lumpy and funny shaped. And they travel through space in an orbit around the sun, so that's a bit planet-like, but their orbital path around the sun is not clear. So in the Earth's orbital path, there's nothing else in that path. We're not going to hit anything. But in Pluto's orbital path, there are lots of other dwarf planets and other objects that it might crash into. So it's been classified as a dwarf planet. So here we've got a little illustration just to put that all into visual context. So we've got the inner planet, we've got the sun here that's emitting all the light. Then we've got the inner planets, Mercury, Venus, Earth and Mars. Then we've got this asteroid belt around here. Then we've got Jupiter, Saturn, Uranus and Neptune. And then in this orbital path here, you've got Pluto, but also not marked on here are loads of other dwarf planets like Ceres and loads of other ones. And you can find out about those on the Near Earth Object NASA website if you're interested. So here's another illustration. This illustration is showing the distances in millions of kilometres between the sun over here and the other planets, so you get a sense of the scale of the solar system. We do need to know the order of the planets, but we've known that for a little while, so I think you'll be fine with that. So it's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And then finally here we've got a table just summarising some of the key details about the different planets in the solar system. So here are the 8 planets. We've got their average distance from the sun during their orbit. So you can see these are, we need a sense of the scale of these numbers. So 58 million kilometres up into 4,500 million kilometres. we've got the time for that planet to orbit the sun, so ranging from 88 days to 165 years. And then we've got the number of moons that that planet has as well. So you can see here we are with our one moon. Venus and Mercury don't have any. Mars has got 2, Jupiter's got 66, Saturn's got 62, Uranus 27 and Neptune 13. So our solar system is a small part of the Milky Way galaxy. So a galaxy is a large group of stars. The Milky Way contains over 200,000 million stars. And our sun is just one of them. So our solar system is just a small part of the Milky Way galaxy. Galaxies can be a variety of shapes, and the Milky Way is a barred spiral arm galaxy. And in fact, the galaxy itself is spinning around. I've included a couple of extra images here. You don't need to worry about learning them or being able to classify galaxies. It's just for your interest, because this is such an interesting area of physics. You can go and do a bit more research. So we've got a picture over here of what we can see of the Milky Way, and you can see this part here. This is the cluster of stars in the Milky Way, and we've got a classification scheme for galaxies here as well. So now we're going to talk a little bit more about why things orbit each other. So why do moons orbit planets, why do planets orbit stars, and why do stars orbit the centre of galaxies if they're spinning and spiralling like in the Milky Way? So the simple answer is that gravity provides a force that allows planets and satellites, whether natural or artificial, to maintain their circular orbits. So let's break that statement down a little bit more. First of all, you can have two types of satellite, natural or artificial. So natural is it's naturally made. Artificial is it's been man-made. So that could be something like the Hubble Space Telescope or a communication satellite, something like that. Now, we know that satellites and planets actually follow slightly elliptical orbits, but they're so close to circular, for the purposes of the GCSE, we can assume that they are circular orbits. Now, and the reason that we can have a circular orbit, so that something can orbit another object in a circle, is because of the force of gravity. So let's have a look at these diagrams in more detail. We've got two here. We've got a diagram of the Earth orbiting the Sun, and we've got a diagram of the Moon orbiting the Earth. Now what's interesting is even though the scales of these diagrams are very different, actually it's the same process that's going on. So let's have a little look in more detail. Here's the Sun and here's the Earth. Now the Earth is moving with a velocity that is shooting off in this direction in a straight line. So at this particular point in its orbit around the Sun, the Earth's velocity is pointing in this direction. Now, if there was no other force acting on the Earth would just shoot off into space like this in a straight line, and it would just carry on. However, there is a force acting on the Earth, and that force is gravity. Now, we know from the work that we've done on forces and third law pairs that this force of gravity acting between the Earth and the Sun is going to act to the centre of mass of the Sun. So you can see here's the force of gravity pointing towards the centre of the orbit. Now, this is the only force acting on the Earth. So we know from our work that we've done on Newton's first law that the forces acting on the Earth are unbalanced, and therefore it should be accelerating, and it is. So you can see that the velocity is going to change direction. So if we look at the Earth a bit further around the orbit now, its velocity is pointing down here, and if there was no force of gravity acting towards the centre of the orbit, the Earth would just shoot off in a straight line like that. So the Earth is accelerating because it's constantly changing direction. There's an unbalanced force of gravity acting on the Earth towards the centre of mass of the Sun, and that unbalanced force causes acceleration. But remember, there's two ways we can accelerate. We can either change speed or we can change direction, because velocity is a vector quantity. And we've got exactly the same thing going on with the Moon orbiting the Earth. The Moon's velocity at this point in the orbit is shooting down here, and if there was no gravity acting, it would just carry on in a straight line with a constant speed. So it wouldn't accelerate. However, there is an unbalanced force acting on the Moon, the force of gravity, which is acting towards the centre of mass of the Earth. And so because the forces are unbalanced, the Moon is going to accelerate. It doesn't change its speed, it just changes its direction. So you can see if we go further around the orbit, here. The velocity of the moon is acting in a straight line again, whoosh, off it would go, but there's gravity acting from the moon towards the centre of mass of the Earth. We've got an unbalanced force, and that is going to cause the moon to change direction. So here we have that explanation in writing. The planet or moon would travel in a straight line, shown by the velocity arrow, if it were not for the force of gravity acting on the planet or moon. The speed of the object orbiting is constant, but the velocity is constantly changing because the direction is changing. Therefore, the planet or moon is accelerating. The forces acting on the planet or moon are unbalanced. The planet or moon is accelerating towards the centre of the orbit. So the acceleration is always in the same direction as the force. So the resultant force on the Earth here is towards the centre of the circle, and so the acceleration is towards the centre of the circle. Now, orbits are quite interesting things, and when we're launching artificial satellites into space to orbit the Earth for, let's say, communications or scientific research, we need to choose how far away from the Earth the orbit is going to be, and we need to choose the speed that we want that satellite to orbit at. And we have to get those two dimensions matched up in order to get what we call a stable orbit. So for a stable orbit, the radius must change if the speed changes. So here we've got satellite S, and we've got the Earth here, and we've got 3 different orbital paths. We've got orbital path A, which is going to crash into the Earth, that's no good. We've got orbital path C, which is going to fly off into space, that's no good either. And we've got orbital path B, where if it's on orbital path B, it will keep orbiting the Earth in a stable orbit. And that's what we want to try and achieve. Okay, this stable orbit, where a satellite will keep orbiting either a planet or a star. So we've just said that orbit B is a stable orbit, and the unstable orbits are A and C. Now it's interesting because in orbit A, the velocity of the satellite is too slow, and so it crashes into the Earth. But in orbit C, the velocity of the satellite is too fast, and so it shoots off and escapes. So we need to find a velocity that's just right for the distance that this satellite is from the Earth. Now, if we change this distance here, we change the velocity needed for a stable orbit. And it's quite an interesting set of calculations that you learn more about the sixth form and you learn how to complete in order to find that velocity needed for that stable orbit at that distance. So if we have an orbit that's closer to the planet or star, we have to have a higher speed stable orbit. So if we took satellite S here and moved it closer to Earth, say here, we would need a higher velocity stable orbit than we do currently when we're out here. And if the orbit moves further away from a planet or star, we need a lower speed stable orbit. So if we were out here, then the stable orbit would be at a lower velocity. So the two change together and go hand in hand. Now, one final thing for you to have a little look at and have a go at, and you'll need to do a little bit of research for this. Hopefully you'll find it quite interesting. I'd like you to do a comparison about the similarities and differences between planets, moons and artificial satellites. So an artificial satellite, remember, is a man-made satellite. So it could be the Hubble Space Telescope, it could be a communication satellite, it could be a scientific research satellite, but it's man-made and it's been put into a stable orbit by us. Whereas a moon is naturally made and has naturally found a stable orbit. So what you're going to do, you can put the differences on the outside of the Venn diagram and the similarities in the overlapping areas. So have a little think about what's similar and different about them. You can think about their sizes, their orbits, their orbital paths, whether they have stable orbits, whether their orbits need maintaining, all those sorts of things. So I hope you found that tutorial video useful. That's the space physics topic completed now. So if you have any questions, please do ask. Try and get all your notes together. I know it's been a bit tricky, so they're in different places. And come to Help Club if you have any questions.